Welcome to my presentation. I'm Janneke Remmers, and I'll be presenting the results of a recently published paper, Can Model Structure Families be Inferred from Model Output? And I wrote this paper together with Jan Teuning and Lieke Melsen. The idea behind this paper was that models, they are black boxes, and often we don't know what happens. We just put in data, let the model run, and then we have the output and we analyze that. And then uncertainty analysis, it is a challenge to do that and to actually get a good quantification, as has already been shown in previous presentations. So we have three different types. We have input, parameter, and model structure uncertainty. Input uncertainty, you can analyze that by either checking your measurement device and getting an estimate of the variance that you could have. Parameter uncertainty, you can have a parameter space that you can define for each parameter, and then you have a set of dimensions that within that you have your uncertainty. Then for model structure, you want to define a same model space. However, that is more difficult and you don't exactly know what the space is. And besides that, you have different types. So it's for all those types, it's difficult to exactly say, okay, what is the boundaries of the model space? So we don't know what it is. And to circumvent this problem, there have been model ensemble runs. And the only problem is these can be biased, that, for example, you have more similar type models than that it's not representative of the full model space. As Knut already showed with the dendrogram he made for climate models, he based this on the model output, and he showed that models that are from the same family are actually clustered together, like here the purple or the red one. Another method is to use a modular model framework. Here you can, they have disassembled existing hydrological models, and then you can build them back up into any model within the limits of that MMF. We tried to combine these two methods, that we build our own models using an MMF, and then based on the output, we try to see, okay, can we relate the output back to what the model structure actually is? For this, we used the Fuse modular model framework. And with that, we made these 8 models using a distance metric and hierarchical structuring. We made this dendrogram, and minimize this, by the way. And then we so we have 3 families. This is the first one, and as you can see, model 1 and 2, they have only one component difference, so they are clustered closely together. Well, if you compare it with the third one, it has more components that differ, and we said that each equation has an equal weight. And then we have the second family and the third family. So we have this dendrogram, and then we ran all of these models for 671 cases in the contiguous US using the CAMELS dataset. We didn't calibrate the models because we didn't want the model structure to be obscured by calibration. We did use, however, a parameter ensemble of 100 parameter sets. Then this model output, to analyze it, we use 8 signatures, 3 timing signatures that are indicated with an H. These were calculated for the discharge, evapotranspiration, and the surface runoff. And also for these 3, we had a magnitude signature, which is indicated with a Y. Then we also had a runoff ratio and the stream flow elasticity. Then based on each of these signatures, we made another dendrogram, which is shown on the right side. Then we can relate both of these dendrograms with each other by correlating them, and we get a big gamma correlation coefficient. I'm going to show two cases now to explain this method a bit further and actually show you how it works in a real case. So this is the first case where we start again with the model structure. Then based on that, we have the timing signature for the discharge. And if we draw lines between those two dendrograms, we see that they align really, really nicely. So if we go back to the output, how that looks, you see that the bands of the model families, model structure families, they are distinct bands, and that explains why we can relate the output to the model structure. And because of this, we have a high correlation coefficient. Then in the second case, we start again with the model structure dendrogram. We get the dendrogram based on the surface runoff magnitude signature, and we draw lines between the different model results. We see that it doesn't align so nicely anymore. And that's also visible in the output, because there the different bands for model structures, they overlap, and this also results in a low correlation coefficient. As I already said, we did this for 671 catchments, and we made box plots for all of them, for all 8 signatures. And as you can see, overall, the correlation coefficient remains quite low. The dotted line, that's our baseline, which we base on the median of the whole model output. And we do see some cases, for example, here with the timing signature of the discharge or the stream flow elasticity that is quite high. Then we tried maybe if two of these signatures can combine, or how will that result in maybe a better correlation coefficient. Unfortunately, that didn't happen. If the correlation coefficient was already high for a single signature, it often remained high when it was combined with other signatures. However, we didn't see any significant improvement in the correlation coefficient when we combined them. Because we do see these high correlation coefficients for some signatures, we thought we would compare them to some climate characteristics. We compared them with aridity, the snow fraction, and the seasonality. And this is just one example where we have the snow fraction and the magnitude signature of the discharge. And as you can see, there's not a real relation between the climate and the correlation coefficient. Overall, we got quite low R-squared values. So as to the discussion, how we did this study setup, we chose one MMF, which was fused. We could have chosen other MMFs as well, for example, Raven or Suma. This might have changed the results. Then the same applies to the signatures. We chose these 8 signatures, but there are, of course, other signatures that could have been chosen, other variables that could have been analyzed. Then finally, how we computed the dendrograms. As I said, we used the distance metric and a hierarchical structuring method. There are several methods, statistical methods that we could have used. We tried 5 for each of them, and each of these methods, they showed a slightly different result from the other. So even the statistical methods that you use, they influence the final results. And in the end, we used the most commonly used statistical method. So then we have the model space that we sampled. We started with the model structure, which is in case the hypothesis model space, but we compared that with the output model space. And these two, as we've shown, are different. There are 2 different things, and we couldn't align them. However, as I showed before, Knutti et al. With the climate models, he was able to at least show that who made the models, that they were clustered together, but we couldn't. But then that could be explained because in Fuse we only have bucket based hydrological models, which is quite a small part of the whole model space. Well, Knut et al. Probably had a much larger part of the whole model space, and then there's probably more chance that he actually gets the different clusters within the whole model space, right? And then secondly, he didn't actually compare it to the model structures because that would have been a large task that was probably outside the scope of his study. And then finally, to say, okay, hypothesis or output, there's quite a difference between that as well. We didn't perform a sensitivity analysis between the two, and that would have probably complicated the whole research more, because then you have to take into account the parameters and the input data as well, and then you have to already analyze the output before you even can make the dendrogram based on the model structures, which is more problematic and complicated, more challenging. And because of that, actually the output model space is a result of the model structure, the hypothesis model space. And because of that, we chose to use the hypothesis model space, besides the fact that if we analyze the hypothesis model space, it's more congruent with how we sample parameter space. So thank you for your attention. And if you want to look up what we've done besides this presentation, you can check out our article. And if you have more questions besides the question that you can pose now, you can always email me there. Thank you.
Okay, thank you very much for a nice presentation. Is there any question from the audience?
I might have a small question. I was wondering, I could not follow completely at the start when you were linking those model structures with the results of the hydrological models. How did you do that exactly? This linking these results?
Yeah. So you mean here where we linked
yes.
Yes. Model structure? I think I can actually better show this one, because you can make a dendrogram based on because for each model, for example, model 8, you get a model output, and then based on that output, you can make all of the signatures, and then for each of those models, so for model 1 to 8, you get the same signature. So in this case, the timing discharge. And then you compare all of those 8 timing discharge with each other. You again calculate a distance metric, and based on that distance metric, you perform a hierarchical structuring, and then you can get this dendrogram. And then if you compare the two dendrograms with each other, you can calculate how well these two dendrograms correlate, and then you can get the correlation coefficient.
Okay, so you somehow get a classification of the output as well.
Yeah.
Okay. Okay.
You have the output for all 8 models, and then you don't. What you would do with maybe a model ensemble is that you average over all of those 8 models. We didn't do that. We kept each model output as it is, and then we compared the model outputs with each other. And in this case, it's the 8 signatures that you get from the 8 models.
Okay, thank you.
Thank you. Is there any other question? We have still some minutes. Can you provide some, just a curiosity, some information about the time for the time span for applying these methods? How is the computational for running these methods?
I think in total the model ran for a bit less than about 6 days, I think, because it was a lot of catchment that it had to process, and then a lot of parameter sets as well that made the computational burden a bit higher.
Okay, so this means that for very high complex models that involve like 100 of model factors, this could be a bottleneck, isn't it?
Yes, it could be.
Okay.
Yeah, but this was a new approach to see if these two methods can be combined, and for that reason we chose to start with relatively simple models to see what the possibilities are.
Okay, yes, using multiple methods in order to reduce the computational time. This is something that should be taken into account for the application of quality models, for instance, and can be a really bottleneck in the application of some methods. So combining multiple approach can be a solution. Is there any other question, curiosity?